Hello there, and welcome. Tonight, I want to take you somewhere that exists between silence and rhythm, between the vastness of space and the intimacy of human curiosity. I want to take you on a journey to explore one of the universe's most profound mysteries, one that scientists have been gently uncovering for decades, and one that might just change the way you think about the cosmos and our place within it. Before we begin, I want you to know that this is a space created just for you. Make yourself comfortable. Perhaps you're lying in bed, or maybe you're sitting somewhere quiet, watching the darkness outside your window. Wherever you are, whatever time it is where you're watching from, we're about to embark on something beautiful together. If you're enjoying this cosmic journey, if you feel that pull of wonder that comes from contemplating the infinite, we'd be deeply grateful if you'd take a moment to like and subscribe. It means so much to us, knowing that there are people out there who feel the same sense of awe about the universe that we do. So please, in the comments below, tell us where you're watching from tonight. What time is it where you are? Are you watching under the stars, or are you watching while the stars watch over you from beyond the horizon? Share that with us. Create a community of cosmic wanderers, all gathered together in this moment, all contemplating the same endless mysteries. Now let me ask you something that might seem simple on the surface, but that opens doorways into worlds of wonder that we've only recently begun to understand. Have you ever truly thought about light? Not just the light that illuminates your day, not the familiar glow of sunset or the comfort of a lamp in a dark room, but light as a fundamental force in the universe. Have you ever considered that somewhere out there, in the vast reaches of space, there are objects that flash this light faster than almost anything we know? What if I told you that throughout the galaxy, there exist cosmic beacons, ancient lighthouses, spinning in the darkness with a precision that makes our most advanced atomic clocks look slow by comparison? What if there were objects flashing their light hundreds of times per second, their signals reaching across the void of space, traveling through the vacuum of the cosmos to eventually touch our instruments here on Earth? It's a question that might seem strange at first, maybe even a bit difficult to believe. But it's a question that has captivated some of the greatest minds in science for generations. It's a question that has led to discoveries that reshape how we understand the fundamental nature of reality itself, the nature of matter at its most extreme, the nature of physics when pushed to its very limits. And it's a question that perhaps holds clues about the very nature of existence and our relationship to the cosmos, about how we fit into this vast web of stellar phenomena and cosmic events that have been unfolding for billions of years. What if, just maybe, the universe had a heartbeat? What if that heartbeat was something we could actually detect? Something that pulsed across the vast distances of space, reaching Earth as regular as clockwork, as predictable as your own heartbeat is to you? What if that heartbeat came from objects so exotic, so extreme, that they exist at the very edge of what physics allows, objects that push the boundaries of our understanding and force us to reconsider what we thought was possible? These are neutron stars, and more specifically, we're going to explore the phenomenon of pulsars, those spinning cosmic lighthouses that flash their beams across the universe with a precision and regularity that is absolutely breathtaking when you truly contemplate it. The discovery of pulsars is one of those moments in science that feels almost like a fairy tale, a story of curiosity leading to wonder, of careful observation revealing secrets that had been written in the cosmos all along. In 1967, a brilliant young astronomer named Jocelyn Bell Burnell noticed something peculiar in her radio telescope data. There were signals coming from somewhere in the heavens, signals that repeated with such perfect regularity that for a moment, the research team wondered if they might have discovered an artificial signal from an extraterrestrial civilization. They even joked about calling it LGM-1, for little green men. But as they investigated further, as they looked more carefully at these strange signals, as they ran the data through their minds again and again, they realized they had stumbled upon something even more profound, a natural cosmic phenomenon that was stranger and more beautiful than anything anyone had anticipated. What they had discovered were pulsars, neutron stars that spin so rapidly that their beams of radiation sweep across space like the beam of a lighthouse, and we on Earth see these as regular pulses of radio waves. These objects, which we now call pulsars, flash their light across space at rates that seem almost impossible to comprehend. Some of them flash dozens of times per second, The fastest ones, called millisecond pulsars, flash hundreds of times per second, faster than you can blink, faster than you can consciously perceive, faster than your eye can follow. Imagine, for a moment, a lighthouse that spins so quickly that from a distance you see not individual flashes but an almost continuous glow, a steady hum of light and energy. Now imagine that light is being emitted not as visible light, but as radio waves and X-rays, traveling across the vast distances of space at the speed of light itself, carrying information encoded in its rhythm, telling us stories about the nature of matter and energy that we're only beginning to understand. Some of these pulsars are so regular, so precise in their rhythms, that they can be used as cosmic clocks, more accurate than any mechanical timepiece we could ever construct. But here's where it becomes truly fascinating, truly worthy of your contemplation in these quiet hours. We now understand why these objects flash at all. We've discovered the mechanisms, the physics, the beautiful dance of matter and energy that causes these cosmic lighthouses to spin and pulse with such incredible precision. We've learned that pulsars are the remnants of massive stars that exploded in supernovae, catastrophic events where a dying star tears itself apart in a brilliant burst of light and energy. And in the core of what remains, in the heart of that stellar death, something extraordinary happens. The core collapses inward with such tremendous force that it creates an object of almost unimaginable density. A single teaspoon of this material would weigh as much as a mountain, as much as billions of tons. This is neutron star material, matter so compressed that the electrons and protons are forced together into neutrons, creating a substance unlike anything we can create in our laboratories on Earth. When these massive stars explode, the core that remains begins to spin faster and faster, much like a spinning ice skater who pulls in their arms and begins to rotate more rapidly. This is due to the conservation of angular momentum, a fundamental principle of physics that says that the rotational momentum of an object must be conserved as it shrinks. So as the stellar core collapses inward, it must spin faster to maintain its angular momentum. And sometimes, when this happens, we get these incredible spinning objects, pulsars that rotate hundreds of times per second, that flash their beams across the cosmos like cosmic lighthouses that never tire, never slow down, never stop their eternal dance. Perhaps you're wondering how we could possibly know all of this. Perhaps you're thinking that surely objects so distant, so remote from our world, must remain forever mysterious and unknowable, wrapped in the secrecy of the vast distances that separate us from them. But that's the beauty of science, and that's one of the reasons we gather here together in this quiet moment to contemplate these mysteries. Through patient observation, through careful measurement, through decades of data collection and analysis, through the dedication of astronomers and physicists working across the world and across generations, we've pieced together the story of pulsars. We've learned not just what they are, but why they behave the way they do. We've learned the mechanisms that cause them to flash, the physics that determines how fast they spin, the reasons why some pulsars have slowed down over millions of years, while others remain spinning at incredible speeds. In the coming hours, we're going to explore this story together in the gentle darkness, allowing our minds to wander through the cosmos, allowing the rhythm of the narrative to guide us deeper into understanding. We're going to begin with the basics, understanding what pulsars actually are, where they come from, and why they're so extraordinarily special. We'll explore the nature of neutron stars, those objects so dense that they represent one of the most extreme states of matter that can exist in the universe. Then we'll move deeper into the mechanisms that make them work, examining the physics that allows these objects to achieve such incredible speeds and such remarkable precision. We'll explore what scientists have discovered through observation and experimentation, and we'll consider what mysteries still remain, what questions we're still asking, what possibilities still lie unexplored in the cosmic darkness. But more than that, we're going to use this exploration as a doorway into deeper contemplation, a space where you can allow your mind to drift and wonder and consider the profound implications of these cosmic phenomena. We're going to think about what it means to live in a universe that produces such wonders, such extraordinary objects, such perfect demonstrations of how nature operates at the extreme edges of what's possible. We're going to consider our place in the cosmos, how we fit into this vast web of stellar phenomena and cosmic events, how we as conscious beings are related to these distant pulsars through the shared atoms that make up all matter, we're going to explore the philosophical implications of understanding more and more about how nature works, while always maintaining that sense of wonder, that awareness that the universe remains far stranger and more beautiful than we can fully comprehend. So as we begin this journey, I want you to understand that this is not just a recitation of facts and figures, not just a collection of scientific information to be memorized and forgotten. This is an invitation to wonder. This is an opportunity to let your mind drift through the cosmos, to contemplate mysteries that have puzzled humanity for generations, to find peace and meaning in the vastness of it all. We're going to move slowly through this material, taking our time, allowing each idea to unfold gently before we move to the next. There will be pauses, moments of silence, spaces for your own contemplation. There will be gentle transitions from one idea to the next, allowing your mind to follow naturally, without strain, without shock, without anything that would disturb your peace or pull you away from the contemplative state we're creating together. Think about why this matters. Think about why you, sitting here right now in this moment, in this place, should care about cosmic lighthouses spinning in distant nebulae, about neutron stars rotating at the edge of the known universe, about radio pulsars reaching across the void of space to touch our instruments here on Earth. It matters because we are made of the same atoms that make up these neutron stars. Every atom in your body was created in the heart of a star, or in the explosion of a supernova, or in the vast clouds of gas and dust that fill the spaces between stars. It matters because understanding the universe helps us understand ourselves, our origins, our connection to everything around us. It matters because the human capacity to ask questions, to seek answers, to contemplate mysteries, that capacity is perhaps the most beautiful thing about being human. We are the universe becoming conscious of itself. We are stardust that has organized itself into patterns complex enough to wonder about its own origins, to look up at the stars and ask why and how, and what does this mean? And pulsars? Pulsars are perhaps one of the most profound demonstrations of this self-awareness in action. They are cosmic clocks, precise beyond measure, tools we can use to test our understanding of physics itself. They are remnants of stellar violence, the remnants of massive stars that exploded in supernova billions of years ago, leaving behind these incredible spinning objects that continue to shine, continue to pulse, continue to tell their story to anyone who knows how to listen. They are laboratories where physics operates at its most extreme, where our theories are tested to their very limits, where we discover that nature is far more capable of extreme behavior than we might have imagined. And they are, in their way, a communication from the universe itself, signals reaching across the void of space, carrying information about how nature works at its most fundamental level, about the rules that govern existence itself. The question at the heart of our journey tonight is simple yet profound. Why do pulsars flash as fast as they do? What causes these objects to spin with such incredible speed? What determines the rate at which they pulse? The rhythm of their cosmic heartbeat? How is it possible for matter to be compressed to such extraordinary densities that it forms objects where a handful of material weighs as much as an entire star? What mechanisms in the universe are capable of spinning these objects hundreds of times per second, and what keeps them spinning at that rate for millions and billions of years? These are the questions that have driven astronomers and physicists to observe the heavens, to collect data, to build theories, to test their ideas against the reality of what we observe in the cosmos. The answer, as we'll discover together in the hours ahead, involves neutron stars, the densest objects in the universe short of black holes. It involves the conservation of angular momentum, the spinning up of these objects as they form from collapsing stellar cores. It involves the conservation of mass and energy, the transformation of potential energy into rotational energy. It involves magnetic fields of unimaginable strength, fields so powerful that they would tear apart any material object on Earth, fields that interact with the rotating matter of neutron stars to create the beams of radiation we observe as pulses. It involves the very nature of space and time, as predicted by Einstein's theory of relativity, which tells us how gravity warps the space around massive objects, and how time itself runs differently in the presence of strong gravitational fields. But perhaps most importantly, it involves us, our curiosity, our desire to understand, our willingness to sit quietly and contemplate the mysteries of existence. Because in understanding pulsars, we're not just understanding distant cosmic objects that have no relevance to our lives here on Earth. We're understanding the universe itself, the fundamental rules that govern how it operates, the mechanisms that have shaped our world, that have created the conditions for life to emerge on this planet, that have made it possible for us, right here and right now, in this moment, to look up at the stars and wonder about their secrets. Every atom in your body was forged in these same cosmic furnaces. Your existence is directly connected to the very phenomena we're about to explore. So settle in, get comfortable. As we move through the hours ahead, allow yourself to drift along with the narrative, to let the rhythms of language mirror the rhythms of pulsars themselves, regular, reliable, beautiful in their precision. Allow the wonder to wash over you like gentle waves on a cosmic shore. Allow yourself to feel small in the face of the cosmic vastness, but also connected, part of something larger and more profound than yourself. Allow your breathing to slow, your heartbeat to steady, your mind to open to the mysteries that await us. We're about to take you on a journey through the cosmos, and we want you to be present for every moment of it, fully aware and deeply relaxed at the same time, open to wonder and at peace with the questions we cannot yet answer. This is our journey together, a journey through darkness illuminated by flashing light, through vast distances crossed by the speed of light itself, through mysteries that science has partially unveiled but will never fully explain. And in travelling together, we create a kind of communion, a shared human experience of contemplation and awe. You're not alone in your wonder. Across the world, in your comments below, you'll find others who feel the same sense of awe that you do right now. So if you're still here with us, if you're following along on this cosmic journey, we'd love to hear from you. Tell us in the comments what aspect of this mystery intrigues you most. Are you fascinated by the extreme density of neutron stars? Does the idea of spinning objects in space capture your imagination? Are you curious about how we can possibly know about objects so far away? Whatever draws you to this mystery, share it with us and with the community of cosmic explorers that's gathering here. Tonight, we contemplate the stars. Tonight, we wonder about the universe. And in that wondering, we find peace, we find meaning, we find our place in the eternal cosmic dance that continues whether we're watching or not. But we are watching. And that fact alone, that conscious observers exist in this universe, capable of understanding and marveling at its workings, might be the greatest mystery of all. As we move forward into the deeper exploration of pulsars and neutron stars, as we begin to examine the evidence that scientists have gathered, as we start to understand the mechanisms that make these objects work, remember that you're participating in humanity's ongoing conversation with the cosmos. You're part of a long tradition of stargazers and seekers, of people who have looked up at the sky and asked profound questions about the nature of reality. Now, let us turn our attention more fully to the universe's fastest beacons, those remarkable objects that have fascinated astronomers since their discovery and continue to reveal new secrets about how the cosmos works. For millions of years, these pulsars have been spinning through the darkness, their beams sweeping across space, and we have only recently, in the last few decades, developed the technology and the understanding to recognize what they are and begin to understand why they behave as they do. The universe has been broadcasting these signals all along, and finally we have learned to listen. When we think about the universe, we often imagine it as a vast and mostly empty place, a darkness punctuated by the light of distant stars and galaxies. We imagine that this emptiness is inert, unchanging, a backdrop against which cosmic events unfold. But this is far from the truth. The universe is dynamic, constantly changing, filled with processes and phenomena happening at scales both infinitesimally small and incomprehensibly large. Everywhere we look, when we develop the tools to see, we find activity, complexity, wonders that seem almost designed to challenge our understanding and expand our imagination. And pulsars are perhaps one of the most spectacular examples of this dynamic, ever-active cosmos. They are not dormant relics left over from ancient stellar explosions. They are active, vibrant objects, constantly converting their internal energy into radiation, constantly pulsing their beams across space, constantly telling us stories about the nature of matter and energy and the fundamental laws that govern the universe. To understand pulsars, we need to start with an understanding of what stars are and how they live and die. Stars are massive spheres of hot gas held together by their own gravity. In their cores, nuclear fusion occurs. Hydrogen atoms are fused together to create helium, releasing tremendous amounts of energy in the process. This energy pushes outward, creating an internal pressure that balances the inward pull of gravity. For most of a star's life, this balance is maintained. The star shines steadily, converting hydrogen into helium, maintaining this beautiful equilibrium between outward pressure and inward gravity. But this equilibrium doesn't last forever. For the most massive stars, stars many times more massive than our Sun, this peaceful state eventually comes to an end. As the star ages, as it burns through its hydrogen fuel and then its helium fuel, as it builds up heavier and heavier elements in its core through nuclear fusion, something catastrophic begins to happen. The star begins to run out of fuel. The nuclear reactions that have been producing the outward pressure that holds the star up against gravity begin to slow down. The balance tips. Gravity begins to win. And when the most massive stars finally run out of fuel, when there's nothing left to stop gravity from pulling inward, the result is one of the most violent events in the universe, a supernova explosion. A supernova is so bright that for a brief moment, a single dying star can outshine an entire galaxy containing billions of stars. The outer layers of the star are blasted outward into space at speeds of thousands of kilometers per second. The energy released is almost incomprehensible. It would take our Sun millions of years to release the same amount of energy that a supernova releases in a few seconds. And in the midst of this violent explosion, something remarkable happens. The core of the star, the innermost part that wasn't blown away, collapses inward with tremendous force. The atoms that make up this core are pressed together more and more tightly until they reach densities that seem impossible, that challenge our very understanding of what matter can be. In this collapsed core, something extraordinary happens. The pressure becomes so intense, the temperature so high, that the normal structure of atoms breaks down. Electrons, which normally orbit nuclei in well-defined energy levels, are forced into the nuclei themselves. They merge with protons to form neutrons. The atoms, in a sense, lose their identity. What remains is a sea of neutrons held together by the strong nuclear force, the same force that holds nuclei together. This is neutron degenerate matter, and it represents one of the most extreme states of matter that can exist in the universe. Picture this density for a moment. A neutron star is so dense that a piece of it the size of a sugar cube would weigh as much as a mountain, billions of tons. A single teaspoon would weigh as much as the entire human population. All the electrons, all the protons, all the complexity of atomic structure is compressed out of existence, leaving only neutrons packed together so tightly that they form a sphere typically only about 20 kilometers across. And yet, if the original star had a mass of perhaps 20 or 30 times the mass of our Sun, it can all collapse down into that sphere of only 20 kilometers in radius. It's as if the entire Earth were compressed into an object the size of a city. The density is almost beyond comprehension. Now, here's where something truly beautiful happens. Remember what we said about the conservation of angular momentum. When a star collapses inward, when its core shrinks down to form a neutron star, the rotation rate must increase to conserve the angular momentum. Think of a spinning ice skater who pulls in their arms. They spin faster. The same principle applies here. A star that was rotating slowly before it exploded might be rotating only once per week or once per month. But when its core collapses down to form a neutron star, that rotation rate increases dramatically. The same amount of angular momentum is now contained in a much smaller object, so it must be rotating much more rapidly. Some neutron stars rotate once per second. Some rotate 10 times per second, and some, the millisecond pulsars that we'll discuss later, rotate hundreds of times per second. And here's the remarkable part. These rotation rates remain remarkably constant over millions of years. A pulsar that rotates 100 times per second today will still be rotating approximately 100 times per second a year from now, or 100 years from now, or even 1,000,000 years from now. This is because there's almost no friction in the vacuum of space to slow them down. They're surrounded by the near-perfect vacuum that exists between stars, and they're losing energy only very slowly through the radiation they emit. So they can maintain their rotation rates for incredibly long periods of time, timescales that dwarf human history, geological history, even the history of life on Earth. As these neutron stars spin, something else remarkable happens. They possess incredibly strong magnetic fields billions of times stronger than anything we can create in our laboratories on Earth. We believe these magnetic fields are inherited from the original star's magnetic field, which gets compressed along with everything else during the collapse. Just as a shrinking conductor compresses the magnetic field lines passing through it, the collapsing stellar core concentrates the magnetic field, making it incredibly intense. And this magnetic field rotating along with the neutron star creates a situation where charged particles near the neutron star's surface are accelerated to tremendous speeds. These particles are funneled along the magnetic field lines toward the magnetic poles of the neutron star, just as Earth's magnetic field funnels charged particles from the solar wind toward Earth's magnetic poles, creating the auroras we see in the night sky. At the neutron star's magnetic poles, these accelerated particles strike the surface and create beams of radiation, radio waves, X-rays, and other forms of electromagnetic energy. And because the magnetic axis of the neutron star is not perfectly aligned with its rotation axis, these beams sweep across space like the beam of a lighthouse. From Earth, we see pulses of radiation each time one of these beams points toward us. The regular pulses we observe are simply the result of this beam sweeping past us again and again as the neutron star rotates. This is the mechanism that creates the pulsar phenomenon that has fascinated astronomers for decades. But why, you might ask, do some pulsars spin so much faster than others? Why do some neutron stars rotate only once per second, while others rotate hundreds of times per second? This is where our understanding of pulsars becomes even more fascinating, where we begin to understand not just what pulsars are, but how they evolve and change over time. Some neutron stars spin slowly because they were formed relatively recently, or because they've been slowing down over millions of years due to the energy they lose through radiation. But others spin incredibly rapidly, and these rapid rotators represent some of the most intriguing objects in the cosmos. The fastest pulsars, the millisecond pulsars, are believed to have been spun up by a companion star. Picture a binary system, two stars orbiting each other. If one of the stars is a neutron star and the other is a regular star that has swollen into a red giant, material from the red giant can begin to flow toward the neutron star. This material, called an accretion disk, spirals inward and gradually deposits angular momentum onto the neutron star, causing it to spin faster and faster. Over millions of years, this process can spin a neutron star up from a rotation rate of once per second to hundreds of rotations per second. The neutron star is literally being spun up by the material falling onto it, like a cosmic top being continuously set spinning faster and faster by the addition of angular momentum. This process, called spin-up or recycling, explains why we observe millisecond pulses in certain types of binary systems, and why these pulses are often associated with companion stars. It also explains why millisecond pulses are among the most stable objects known. Their rotation rates can be measured with extraordinary precision, making them useful tools for testing theories in physics and even for detecting gravitational waves. A millisecond pulsar is a cosmic clock of almost supernatural precision, and we use these clocks to probe the deepest mysteries of the universe. Consider for a moment what this all means. We have objects, neutron stars, that are so dense that their entire mass is concentrated in an area the size of a city. We have objects that are rotating at rates that would tear apart any ordinary material object. We have objects whose magnetic fields are strong enough to affect the behavior of matter across distances of thousands of kilometers, and we have objects that maintain their rotation with a precision that rivals our most advanced atomic clocks. These are not the products of theory alone. They're real objects that we can observe, that we can measure, that we can study with our telescopes and our instruments. And this is just the beginning of our understanding of pulsars. As we move deeper into our exploration, as we examine the evidence that astronomers have gathered through decades of careful observation, as we consider what these objects tell us about the nature of matter and energy and the fundamental laws of physics, the wonder will only grow. The universe is far more capable of producing extreme and magnificent objects than most people realize, and pulsars are perfect examples of this truth. If you're still with us, if you're following along on this journey through the cosmos, if the mysteries of pulsars and neutron stars are captivating your imagination, we'd love to hear from you. What have you found most interesting so far? Are you fascinated by the idea of matter being compressed to such extraordinary densities? Does the concept of objects spinning hundreds of times per second capture your imagination? Are you intrigued by the mechanisms that cause these objects to spin so rapidly? Whatever aspect of this mystery speaks to you, please share it with us in the comments. Tell us where you are in the world, what draws you to these cosmic mysteries, what questions are forming in your mind as you contemplate the nature of pulsars and neutron stars. By sharing your thoughts, you're adding your voice to a global community of people who are fascinated by the wonders of the cosmos. We've barely begun our exploration, and already we've encountered objects that challenge our imagination and expand our understanding of what the universe is capable of creating. And as we move forward, as we delve deeper into the mechanisms that make pulsars work, as we examine the evidence that scientists have gathered and the theories they've developed to explain what they observe, the fascination will only deepen. We're going to explore the physics of rotation at extreme speeds. We're going to discuss magnetic fields of unimaginable strength. We're going to consider how matter behaves under conditions of extraordinary density and pressure. And we're going to do all of this in the gentle darkness of this contemplative space we've created together, allowing our minds to wander through the cosmos, to ask profound questions, to find peace in the vastness of it all. The universe, in its infinite complexity and beauty, has written a remarkable story in the cosmos. Pulsars are chapters in that story, remarkable demonstrations of how far nature can push the boundaries of what seems possible. They are reminders that reality is far stranger and more wonderful than we can fully comprehend, that the cosmos is filled with wonders waiting to be discovered and understood. And as we continue our journey together, we're going to explore these wonders more deeply, allowing ourselves to be amazed, to be humbled, to feel that profound sense of awe that comes from truly contemplating the vastness of the universe and our small but significant place within it. When light dances faster than thought itself, when the very fabric of time seems to bend under the weight of cosmic forces, we find ourselves contemplating some of the most remarkable phenomena that the universe has to offer. The flashing of pulsars, those rapid-fire beams of radiation that sweep across the vast distances of space, represent something truly extraordinary. A demonstration of just how extreme the conditions in our cosmos can become, how far matter can be pushed before it breaks the conventional rules we've learned to expect from the physical world. And as we settle deeper into our exploration, as we allow our minds to drift through the implications of what we've already learned, we come to understand that these flashing lights are far more than simple cosmic curiosities. They are windows into the fundamental nature of reality itself. Think about what speed means to us here on Earth. We measure the speed of a racing car in kilometers per hour, perhaps reaching speeds of 300 kilometers per hour on a track. We measure the speed of an airplane in similar units, perhaps reaching 900 kilometers per hour at cruising altitude. We marvel at the speed of sound, traveling at about 1,300 kilometers per hour. These are the speeds that dominate our everyday experience. But when we begin to contemplate the speeds at which pulsars rotate, we enter a realm where conventional measurement becomes almost meaningless. We must shift our perspective entirely, must allow our minds to expand to encompass scales that seem almost impossible. A millisecond pulsar rotates approximately 300 times per second. Let that sink in for a moment. 300 complete rotations per second. That means that at the equator of this neutron star, this object only about 20 kilometers across, the surface is moving at a speed of approximately 1/10 the speed of light. The speed of light is the fastest speed anything can move in the universe. Nothing can exceed it. It's the cosmic speed limit. And here we have matter at the surface of a neutron star moving at 10% of that ultimate limit, completing a full rotation hundreds of times per second. It's a speed that seems almost incomprehensible, a pace of rotation that defies our everyday intuition about how matter should behave. Now consider the rotational energy involved in such a phenomenon. When an object rotates, it possesses kinetic energy, the energy of its motion. The faster it rotates, the more kinetic energy it contains. For a neutron star spinning hundreds of times per second, the amount of rotational energy contained in that object is truly staggering. We're talking about energy that would be released if billions of nuclear bombs were detonated simultaneously. This energy is stored within the neutron star, contained by the intense gravity that holds the object together, and yet it doesn't destroy the neutron star. Instead, the object maintains its integrity, continues its rotation, continues to shine with the light powered by this vast reservoir of rotational energy. What makes this even more remarkable is the gravitational field at the surface of a neutron star. The gravity there is so intense that if an object were to fall from a height of just 1 meter onto the neutron star's surface, it would be traveling at approximately 2,000 kilometers per second when it hit. That's about 1% the speed of light. The impact energy would be absolutely catastrophic, releasing far more energy than any explosion we could create on Earth. And yet, the neutron star's gravity is somehow balanced by the pressure of the degenerate matter within it. The material doesn't collapse further. It maintains its structure, continues to exist, continues to rotate at these incredible speeds. The magnetic fields at the surface of neutron stars are equally extraordinary. We mentioned earlier that these magnetic fields are billions of times stronger than anything we can create in our laboratories. But what does that really mean? What are the practical implications of such a powerful magnetic field? To understand this, let's think about magnetic fields here on Earth. Our planet has a magnetic field that protects us from the solar wind, from the stream of charged particles constantly flowing outward from the sun. This magnetic field extends thousands of kilometers into space, creating a protective bubble around our planet. It's strong enough to align compass needles and guide migrating birds, but it's incredibly weak compared to the magnetic fields that exist at the surface of neutron stars. If you could somehow transport a typical bar magnet to the surface of a neutron star, it would be instantly torn apart. The magnetic field gradient, the rate at which the field strength changes with distance, would be so intense that different parts of the magnet would experience different forces, and the magnet would be ripped to shreds. Even individual atoms would be distorted, stretched, and compressed by the magnetic field. The electrons orbiting atoms would be forced into particular states, their normal energy levels completely disrupted. Matter wouldn't behave the way we normally expect it to behave. It would take on properties that seem almost alien to our everyday experience. This is the environment in which pulsars exist. This is the realm of extreme physics, where our normal understanding of how the universe works is pushed to its very limits. And yet, we can observe these objects. We can measure their properties. We can understand, at least in broad outline, why they behave the way they do. The fact that we can do this is a testament to the power of the scientific method, to human curiosity and ingenuity, to our ability to ask questions about the universe and find ways to answer them. So how fast can a pulsar actually rotate? Is there a limit to how quickly a neutron star can spin before it breaks apart? This is a fascinating question, and the answer tells us something profound about the nature of matter itself. At the equator of a neutron star, centrifugal force, the outward force due to rotation, increases with the square of the rotation rate. The faster the neutron star spins, the stronger this outward force becomes. Eventually, if a neutron star were spinning fast enough, the centrifugal force at the equator would exceed the gravitational force holding the material together. When this happens, material at the equator would begin to be flung off into space. The neutron star couldn't spin any faster without literally breaking apart and shedding its outer layers. Based on calculations of the strength of neutron degenerate matter and the gravitational forces at work, astronomers estimate that the theoretical maximum rotation rate for a neutron star is somewhere around 1,000 rotations per second. This would correspond to a speed at the equator approaching 1/3 the speed of light, approximately 100,000 kilometers per second. And remarkably, we've observed pulsars that spin at rates approaching this theoretical limit. The fastest pulsar known, as of our knowledge cutoff, rotates at a rate of more than 700 times per second. This object is spinning so rapidly that if the Sun were replaced with this neutron star, and Earth were placed at the same orbital distance, our planet would orbit around the neutron star many thousands of times before the neutron star completed even one single rotation relative to the fixed stars. Think about that for a moment. The fastest pulsar we know of rotates so rapidly that it would complete 700 revolutions, while the Moon is completing a single orbit around the Earth. It would spin 700 times while the Earth rotates once. It would complete 700 rotations while you read these words. It's a speed of rotation that seems almost impossible, that challenges our ability to visualize what's actually happening. And yet we know that this is real. We've measured it. We've confirmed it through multiple observations. It's one of the most spectacular demonstrations of the universe's capability to push matter and energy to extremes that we can barely comprehend. What causes some pulsars to spin so much faster than others? We've already touched on this question, but let's explore it more deeply now. When a massive star explodes as a supernova and leaves behind a neutron star, that neutron star is born with some initial rotation rate, perhaps once per second, perhaps a few times per second, depending on the rotation rate of the original star and the details of the collapse process. But this is not necessarily the end of the story for that neutron star. If it exists in a binary system, if it has a companion star, then material can gradually be pulled from that companion star and deposit onto the neutron star's surface. This process, which we call accretion, gradually spins up the neutron star. Over millions of years, the neutron star can be spun up from a rotation rate of once per second to hundreds of times per second. The companion star in these systems is often a low-mass star, perhaps a tenth the mass of the Sun. As the neutron star's gravity pulls material from this companion, the material doesn't fall directly onto the neutron star. Instead, it spirals inward in an accretion disk, gradually losing energy through friction and radiation, and gradually spiraling closer to the neutron star's surface. As this material approaches the neutron star and falls onto its surface, it deposits its angular momentum into the neutron star, causing it to spin faster. The process is slow. It takes millions of years to significantly increase the rotation rate, but given enough time, a neutron star can be spun up to extraordinary speeds. This process explains an important feature of pulsar populations that astronomers have observed. Young pulsars, those created relatively recently in the cosmic scheme of things, typically have rotation rates of once per second to a few times per second. These are pulsars that have slowed down from their initial spin-up through the radiation they emit. Older pulsars, those that have had longer to radiate away their energy, spin even more slowly, perhaps once per 10 seconds or once per minute. But the millisecond pulsars, those spinning hundreds of times per second, are believed to be old pulsars that have been spun back up again by accreting material from a companion star. In a sense, they are recycled pulsars, pulsars that have been given new life, new rotational energy, by the material flowing onto them from a neighboring star. This recycling process has profound implications for our understanding of pulsar evolution and the history of binary star systems in our galaxy. It means that the oldest and most rapidly rotating pulsars are not necessarily the youngest. They're the ones that have undergone this spin-up process. It means that the universe has mechanisms for creating objects of almost unimaginable rotational speeds and maintaining those speeds for millions of years. It means that the cosmos is far more dynamic, far more capable of creating extreme objects than we might naively expect. Now let's consider what happens when light is emitted from the surface of a rotating neutron star. The light that's being radiated away comes from the infalling material striking the neutron star's surface, from the heating caused by gravitational compression, from the energy released by the magnetic field interactions. This light carries away energy, and therefore also carries away angular momentum. Over time, this process causes the neutron star to slow down. Without the input of new angular momentum from accreting material, a pulsar will gradually slow its rotation rate over millions and billions of years. The oldest pulsars in the universe are probably quite slow, perhaps rotating once per several seconds or even more slowly. But this loss of rotational energy is incredibly slow. Even for pulsars that are not receiving material from a companion star, the slowing down is so gradual that we can barely measure it directly. A typical pulsar might slow down by a few hundredths of a second per decade, an absolutely minuscule rate of change. Only for the fastest pulsars, those radiating the most energy, do we see measurable changes in rotation rate over the timescale of human observation. This slow loss of energy is why pulsars can maintain their rotation for such incredibly long periods of time. Why a pulsar born billions of years ago can still be spinning today, still be broadcasting its signals across the cosmos, still be available for us to observe and study. The precision of pulsar rotation is something that deserves its own contemplation. We mentioned that millisecond pulsars can be used as cosmic clocks, tools for measuring time with a precision that rivals atomic clocks. But what does this really mean? How can a spinning object possibly maintain its rotation with such incredible precision? The answer lies in the properties of neutron degenerate matter and the very nature of the rotating neutron star as a physical object. Because there's essentially no friction in the vacuum of space, because the neutron star is surrounded by near-perfect vacuum and is losing energy only very slowly through radiation. Once it begins to rotate at a particular rate, it continues to rotate at that rate with remarkable consistency. Small perturbations, such as starquakes in the neutron star's crust or interactions with a companion star, can occasionally cause small changes in rotation rate, but these are rare events that can sometimes be directly observed and measured. A millisecond pulsar might have a rotation period that varies by only a few microseconds over the course of a year. A microsecond is 1/1,000,000th of a second. That means the pulsar is completing 700 rotations per second, and the time it takes to complete each rotation varies by only a few millionths of a second across an entire year. This is a stability that's almost incomprehensible, a demonstration of the absolute reliability of these cosmic objects. In fact, millisecond pulsars are so stable that astronomers have proposed using them as a galactic positioning system, similar to how we use satellites and atomic clocks for the global positioning system here on Earth. We could use millisecond pulsars to navigate through the galaxy, using their incredibly precise timing as reference signals. When we contemplate the implications of these cosmic facts, when we allow ourselves to truly grasp what's happening in the universe, we begin to feel a sense of profound awe. Here are objects, far away from Earth, completely beyond our ability to touch or manipulate, existing under conditions of such extremity that we can't even fully imagine them, and yet we can measure them. We can predict their behavior. We can understand, at least in broad outline, why they behave as they do. This understanding is the result of centuries of human curiosity, of patient observation, of brilliant theoretical work by physicists and astronomers around the world. It's a testament to the power of the human mind, to our ability to ask questions and find answers, to our willingness to explore and understand the universe around us. The beams of radiation emitted by pulsars are themselves remarkable phenomena. These beams are created by charged particles accelerated along the magnetic field lines of the neutron star, and they carry away tremendous amounts of energy. A typical pulsar might radiate as much energy as the sun in the form of electromagnetic waves, radio waves, X-rays, gamma rays, all concentrated in a narrow beam that sweeps across space like a lighthouse beam. Some pulsars are so luminous that they're among the brightest objects in the universe, at least in terms of the energy they emit per unit of time. A few pulsars are so bright that we can detect their radiation even from pulsars located on the opposite side of the Milky Way galaxy, thousands of light years away. The different wavelengths at which pulsars emit radiation tell us different things about the physics happening at and near the neutron star's surface. Radio waves, the longest wavelengths, are typically emitted from regions farther from the neutron star's surface, where the energy density is lower and the radiation can escape into space. X-rays and gamma rays, much shorter wavelengths representing far higher energy photons, come from regions closer to the neutron star's surface, where particles are accelerated to higher speeds and radiate at higher frequencies. By studying pulsars across the entire spectrum of electromagnetic radiation, from the longest radio waves to the shortest gamma rays, astronomers can build a complete picture of what's happening at and around the neutron star. Some of the most remarkable pulsars are those that pulse in gamma rays. Gamma rays are the highest energy form of electromagnetic radiation, carrying far more energy per photon than visible light or radio waves. A pulsar that emits gamma rays must be creating extremely energetic phenomena, perhaps particles being accelerated nearly to the speed of light, perhaps exotic processes involving the neutron star's magnetic field that we're only beginning to understand. When the Fermi Gamma Ray Space Telescope began mapping the gamma ray sky in the late 2000s, it discovered many previously unknown pulsars that emit primarily in gamma rays. Some of these pulsars had been known from their radio emissions but showed up in the Fermi data as well. Others were completely new discoveries, identified initially through their gamma ray emission and then later confirmed as pulsars through other observations. These gamma-ray pulsars are helping to push our understanding of how matter and energy interact at the extreme conditions found near neutron stars. Perhaps you're wondering how we can possibly know all these details about objects that are so incredibly distant, so far beyond our ability to reach or directly examine. The answer lies in the power of electromagnetic radiation and our ability to detect it across the entire spectrum. Light, in all its forms, radio waves, visible light, X-rays, gamma rays, travels at the same speed, the speed of light itself. When a pulsar emits radiation, that radiation carries information encoded in its intensity its frequency, its polarization, its timing. Over the course of hours or days or weeks of observation, astronomers collect thousands or millions of individual photons from a distant pulsar. They measure the precise arrival times of these photons. They measure their energies. They measure their polarization, the direction in which the electric and magnetic fields are oscillating. By analyzing all of this information, by using sophisticated computers to process the data, astronomers can reconstruct a picture of what's happening at the neutron star. They can map the magnetic field. They can understand the geometry of the emission region. They can measure the neutron star's rotation rate with incredible precision. The precision of timing measurements that modern astronomy allows us to make is truly extraordinary. We can measure the arrival time of radio pulses from a pulsar and determine whether that arrival time has changed by even a millionth of a second compared to our predictions. This ability to measure timing with such precision has led to some of the most important recent discoveries in pulsar science. For instance, many pulsars are part of binary systems, systems with two stars orbiting each other. As the pulsar orbits its companion star, the pulsar's distance from Earth changes very slightly. This causes slight variations in the arrival times of the pulsar's signals due to light travel time differences. By carefully measuring these timing variations, astronomers can determine the orbital parameters of the binary system, the orbital period, the eccentricity, the masses of the stars. In some cases, this has allowed astronomers to discover that pulsars are orbited by planets, real planets, like those orbiting stars in our own neighborhood of the galaxy. We've also used pulsar timing to detect gravitational waves. In 1974, a pulsar in a close binary system with another neutron star was observed to be gradually losing orbital energy. The orbit was decaying. The two neutron stars were spiraling closer together. This decay was exactly as predicted by Einstein's theory of general relativity, which says that accelerating masses radiate gravitational waves, and these waves carry away energy and angular momentum. By carefully monitoring the pulsar's timing over decades, astronomers were able to measure the rate of orbital decay and confirm that it matched the prediction of general relativity to remarkable precision. This observation provided the first evidence for the existence of gravitational waves, decades before the direct detection of gravitational waves was finally achieved with laser interferometer detectors in 2015. It's a beautiful example of how pulsar observations have contributed to some of the most fundamental discoveries in physics. The study of pulsars has also revealed the existence of planets around other stars. While most planets around distant stars have been discovered through other methods, detecting the slight dimming of a star's light as a planet passes in front of it, or detecting the slight back-and-forth motion of a star caused by a planet's gravitational pull, some of the first planet discoveries were made around pulsars. A pulsar in a constellation called Virgo was observed to have timing irregularities that could only be explained by the presence of planets orbiting around it. These weren't discovered in the usual way, through direct observation of starlight, but rather through the subtle effects they had on the timing of the pulsar's signals. This discovery was remarkable because it showed that planets could exist even in such extreme environments, and it raised profound questions about how planets form and how common they might be throughout the universe. If you're still here with us, if you've been following along on this journey through the cosmos, contemplating the nature of pulsars and the incredible speeds and energies involved in these cosmic phenomena, we want to know what you're thinking. What has captured your imagination the most? Are you fascinated by the idea of matter rotating at 1/10 the speed of light? Does the concept of using pulsars to detect gravitational waves intrigue you? Are you amazed by the precision with which we can measure the properties of distant objects? Whatever draws you into this mystery, please share it with us in the comments. Tell us what you find most interesting. What questions are forming in your mind? What aspects of this cosmic dance are calling to your sense of wonder? Your thoughts matter, and by sharing them, you're contributing to a global conversation about the nature of the universe and our place within it. As we move deeper into our exploration, as we continue to contemplate the mechanisms that make pulsars work, the mysteries that surround them, and the profound implications of their existence, we're going to encounter questions that push the very boundaries of what we know and understand. We're going to examine evidence that has been carefully gathered by astronomers working with some of the most sophisticated instruments ever built. We're going to consider possibilities and interpretations that might change how you think about matter, energy, and the fundamental nature of reality itself. And we're going to do all of this together in this contemplative space we've created, maintaining that sense of peaceful wonder that allows us to truly absorb the magnificence of the cosmos. There's something deeply humbling about contemplating the rotation of pulsars, the speeds at which these objects spin, the energies they contain, the distances at which they exist from our world. It reminds us of how small we are, how brief our lives are compared to the timescales over which the universe operates, how young our species is compared to the age of the cosmos. And yet, at the same time, there's something profoundly meaningful about the fact that we can understand these objects, that we can measure them, that we can use them as tools to probe deeper into the mysteries of reality. We are, in a sense, part of the universe studying itself, consciousness studying the cosmos that gave birth to consciousness. And that's a beautiful thing to contemplate. The evidence for what we've been discussing, the reality of pulsars, their rotation rates, their magnetic fields, their composition, comes from decades of careful observation using some of the most sensitive instruments ever constructed. Radio telescopes around the world, space-based X-ray observatories, gamma-ray detectors, all working together to gather data about these distant objects. And from this data, a coherent picture has emerged, a story that explains what we observe and helps us understand the universe better. That story is what we're about to explore in much greater depth. We're going to examine the evidence that supports our understanding, we're going to consider what we know with confidence and what remains uncertain, and we're going to marvel at the ingenuity of the scientists and engineers who have made all of this possible. The universe continues to broadcast its signals, to send its messages across the vast distances of space, and we continue to listen, to learn, to grow in our understanding of how reality works at the deepest levels. The pulsars, those cosmic lighthouses that have been spinning in the darkness for millions of years, have so much yet to teach us, so many mysteries yet to reveal. And as we settle deeper into contemplation of these wonders, as we allow our minds to expand to embrace the scale and complexity of what we're studying, we find that the cosmos becomes not more frightening or alienating, but more beautiful, more meaningful, more worthy of our attention and our awe. The spinning stars call to us across the vast distances, and we answer by listening, by learning, by allowing ourselves to be transformed by the encounter with something so far beyond our everyday experience, yet so fundamentally connected to who we are and what we're made of. The evidence that changed everything, the observations and discoveries that fundamentally altered our understanding of pulsars and neutron stars, now awaits our exploration. These are stories of human ingenuity, of careful observation, of brilliant theoretical work, of technology pushing the boundaries of what's possible. They are stories that show how science advances, not through sudden revelations, but through patient accumulation of evidence, careful testing of hypotheses, willingness to revise our understanding when new data demands it. And they are stories that ultimately lead us to a deeper understanding of the universe and our place within it. So let us turn our attention now to this evidence. Let's examine what we know and how we came to know it. Let us marvel at the cosmic mysteries that have been unveiled through human dedication and curiosity. The journey continues, and with each step we take deeper into understanding, we find more reasons to wonder, more reasons to be grateful for the remarkable universe we inhabit, more reasons to feel connected to the vast cosmic dance that surrounds us and includes us. We are made of stardust, and the stars themselves reveal their secrets to us if we are patient enough to listen, careful enough to observe, and humble enough to admit that there is always more to learn, always deeper mysteries to contemplate, always further horizons to explore,